Number 11. Given f of x equals 3 to the x, write function rules for g of x, h of x, and k of x based on the descriptions for part A and C. So here we're going to be talking about different transformations of exponential functions. So recall the general form for the transformations of an exponential function is a times b to the x minus h plus k, where a represents a vertical stretch or shrink, so it's either going to get wider or more narrow depending on what a is. H is a horizontal shift, so left and right, and k moves it up and down. So for example, a, where they ask for g of x, which would be a transformation of 3 to the power of x left 2 units. Well, you need to remember that if it's going left, that's going to be some sort of h value, and if it's going left, your h is negative 2. So when you plug that into the formula, what it looks like is 3 to the x, and I'm supposed to subtract h from x. So minus a negative 2. So that's a little ugly. I'd rather clean that up a little bit to just make it g of x equals 3 to the x. When I subtract a negative number, it's the same thing as adding a positive number. So my final answer would be 3 to the x plus 2. So that's why when we see plus in the equation, we know that it moves it left 2 units. If instead this was a shift to the right 2, that would just be x minus 2 in the exponent. For part B, they're asking for a translation down 7 units. That's telling me that my k value is going to be negative 7, because I'm taking all of my f of x values and I'm just pushing them down 7 units. So h of x would still be equal to 3 to the power of x, that doesn't change, minus 7 at the end. So it says take all of the 3 to the power of x points and just subtract 7 from them. For part C, they ask for a translation right 4 units, so they want h to be equal to 4, and a vertical shrink by a factor of 0.4. So if it's a vertical stretch or shrink, they're telling me what the a value is there. So a is 0.4 in this case. So I don't have a k value, so my k value is just 0. I don't need to worry about adding or subtracting anything at the end. So I could just start substituting it. K of x is equal to 0.4. Remember, the a value is always what you multiply out in front, times 3 to the x. And now it says right 4 units, so I'm going to subtract that h value of 4, and that's it. So this would be a function that is a vertical shrink, so it pushes it down on itself. So it'd be, instead of shooting up that fast, it might be a little bit wider, just because it's like if I pushed it from the top and bottom inward on itself. And it moved right 4 units. So you could always double check yourself just by plugging 3 to the x into your calculator, plug that into y1, and plug into y2 each of these functions, g of x, h of x, and k of x, just to make sure it has the effect that you intended. So for example, for part A, if you had x minus 2 here, you'd see that when you'd graph it, here's your original function, and here's your new function. So obviously you went in the wrong direction there. So just keep that in mind as you're going through these. Number 12. Write the exponential equation that is represented in the table below. Explain how you arrived at your answer. Okay, so they give me a table of values right here, and they want me to go from a table to an equation. Anytime you're asked to do that, the easiest way to do that is to use your calculator. And here we're going to find the exponential regression equation. And we just plug these inputs, these hours, into L1 in our calculator. These will represent the x values. And we plug those bacteria into L2, and those represent our y values. So if you don't remember how to get there, here I am at the home screen here. This is some sort of statistical measure. So I'm going to hit Stat, and I'm going to edit my lists. So I have L1 and L2 here. So I'm just going to type in all of these hours into L1 and all of these bacteria into L2. Just make sure to hit Enter after you type in each value. Now, if you already have something in L1 or L2, just scroll up to highlight L1 And if you hit clear and then enter, that's going to clear all those values out of that list. So I'm going to input them right here. Okay, so I've got all of my x values into L1 and all of my y values into L2. I always just like to scroll through and double check once I'm done that I have the same amount of x values and y values and that I inputted everything exactly how it appears in the table here. And I did. So once I have that, I hit the stat button one more time, I arrow over to calc, and I know this is supposed to be an exponential equation. So I want to find something that mentions exponential here. So there's nothing on the first page. But if you scroll down a little bit to 0, you'll see expreg. That stands for exponential regression. So hit enter there. Depending on what your calculator is updated with, you could have a different screen than mine. But if you just hit enter a couple times, it'll bring you to this screen right here, where you have an a value and a b value. So it tells you the equation is going to look something like this. Y equals a times b to the x, and it gives you an a value of 399.57. I'm going to round to the 100th place here. If they don't tell you, the 100th place is always a good bet to go out to. And 1.1, that 8 would round up to a 9 because of the 9 right next to it. Okay, so I have an a and a b value here. I can substitute those straight into the equation. So the function would look something like this. Y equals, my a value is 399.57 times 1.19 to the power of x. So remember, this represents your starting value here, so your calculator did a pretty good job of estimating that. So it's just giving you an exponential equation of best fit here. So it's going to be pretty close to all of these points here. And that 1.19 represents the growth factor, or the base that you're multiplying by over and over again. So in this case, it's like you're taking 1 and adding 0.19 to it. So it's like you're increasing by 19% each hour with these amounts of bacteria. So just keep that in mind. They don't ask what these numbers mean, but in case you needed to, make sure that you can still recognize that this problem is really no different than the other exponential equations we work with. If they want us to explain how we arrived at our answer, we would just explain what we did in the calculator. We plug the hours into L1. We plug the bacteria into L2. Then we hit stat. And we went over to exponential regression. And you would just describe your process of getting everything in the calculator. So you could check the key on the e-board for the specifics of what you can write for that. So this is number 1 on the last page of the packet. Given y equals 3 to the power of x, evaluate y when x equals 3, and then again when x equals -2, and when x equals 0. So this is just telling you to plug into that equation right there to see what you get. So y equals 3 to the 3rd power. Well, 3 times 3 is 9, and 9 times 3 is 27. So when I raise 3 to the 3rd power, I get 27. For letter B, notice that there's a negative exponent here. When we have a negative exponent, that means the base is in the wrong place. So 3 to the -2nd is the same thing as 1 over 3 squared. So remember, that's how we fix negative exponents. And 3 squared is just 9. Now, when you do this in your calculator, you might get 0.1 repeating. So when I go to my calculator, if I type in 3 to the -2nd power and hit enter, I get that 0.111 repeating. And to convert that to a fraction, I just hit math, enter, enter. That'll always convert whatever decimal you have to a fraction. And for part C, when x is 0, well, we already know that anything to the 0 power is 1, so that one's pretty straightforward. Again, if you don't remember that, just plug 3 to the 0 power in your calculator and it'll spit out 1. Number 2, with the graph of y equals 0.5 to the x power, show exponential growth or decay. So is it going to look like this, or is it going to look like this? Well, the way we look at that is we look at this base right here, this growth factor. If that base b is greater than 1, then it represents growth. And if it's between 0 and 1, then it represents decay. So in this case, 0.5 is certainly between 0 and 1, So it must be decay here, because 0.5 is between 0 and 1. If you think about that, 0.5 is the same thing as 1/2. If I multiplied something by 1/2 over and over and over again, the value goes from this to this to this to this. So it halves every time and it gets smaller. So keep that in mind when you're examining growth versus decay. For number 3, on the other hand, if I multiply something by 1.5 over and over again, it gains 50% of its value. So if this is how much money I would have this much my next time, and then this much my next time. So since this growth factor, or this base, is greater than 1, that means this is going to represent a growth. Number 4, the equation y equals a to the x will be exponential when a equals, let's think about this. Let's try answer choice A. Y equals -1 to the power of x. If I raise -1 to the x power, remember that exponential growth is going to look like this if I graph it. And exponential decay is going to look something like this if I graph it. But if I think about -1 to the x, well, -1 to the first is just -1. -1 to the second, a negative times a negative is positive, so it'd be +1. And then if I raise it to the third power, a negative times a negative is positive, times another negative would be negative again. And if you start to see a pattern here, -1 to the fourth, if you plug that into the calculator, or if you think about, well, a negative times a negative would give me a positive, and another negative times another negative would give me another positive. So that would be positive. Notice that it's just alternating between -1 and 1, -1 and 1. So that doesn't sound like an exponential growth or decay to me. And if I try 0 to the x, so that's what I try instead, y equals 0 to the power of x. Well, 0 to any power is just 0. So that's not going up or down. And a similar argument for 1 to the x. Regardless of what exponent I raise 1 to, I'm always just going to get y equals 1 out of there. So that doesn't represent growth or decay either. But answer choice D, 2 to the x, would be if I multiply something by 2 over and over again. And as we've seen earlier in this packet, that just represents an exponential growth. For number 5, if they're asking about the graph of 3 to the x, that looks very similar to the graph of 2 to the x, where it just starts over here and increases exponentially as we move to the right. So remember, the quadrants are labeled in counterclockwise order, 1, 2, 3, and 4. And this graph lies only in quadrants 1 and 2. The reason that happens is because the range for this function is just from 0 to infinity. There's no value that we could plug into x for 3 to the x to make it equal to 0 to get it to hit the x-axis, or to get it to be negative to get it to go below the x-axis. Even if we try a negative exponent, something like, I don't know, 3 to the -100. That's the same thing as 1 over 3 to the 100, which is just 1 over some huge number, which when I evaluate that is going to get me something super duper small. So even though when you plug this into your calculator, it's going to be something so close to 0, it's not quite 0. And there's nothing you can find that's going to make it equal to 0 or go below 0, so you're stuck only in quadrants 1 and 2, where the y values are positive. Number 6. Which ordered pair represents the y-intercept for the function y equals 5 to the power of x? Well, if I go to graph this in my calculator, it looks something like this, and it's got a y-intercept here. And you need to ask yourself, what is my x value when I'm on the y-axis? If I'm on the y-axis, I haven't moved right and I haven't moved left, so my x value is just 0. If you wanted to go to your table in your graph, you absolutely could, but I'm just going to find this by plugging 0 in for x into my function. And remember that 5 to the 0 power is still just 1. So my y coordinate when I'm on the y-axis is going to be 1. Answer choice C.